keeping it standing on the GL with an inclination. At least you can guess.
Gravity, sir.
Yeah, somebody is about to say something.
Gravity.
Gravity. Who is that? Who said that gravity?
Harshita Katuru.
Okay, Harshita Katuri. Okay. Do you mean to say this is having this is having gravity? This is also having gravity. But what? How does it different? How many of you have studied the concept of center of gravity? I think this is nothing new to you. Center of gravity.
Yes, sir.
You studied. Okay. Just I'm giving an example. This is a standard example in any textbook. You know a funnel. Okay, this is an inverted funnel. And other way around. If you make this thing to stand on a plane surface, and if you make this thing to stand on a plane surface, which one is stable?
First one, sir.
First one is stable, right? Okay.
Yes.
The second one, why it is not stable? Or other way around. If we just give a small tilt, then like a small push, it will trip, right? Why?
So at the base, the area is less compared to the first one. Sir.
Okay, that is one way of looking at it. The other way is the center of gravity falling within the base? And suppose with a slight movement, of course, because the base is more, even if you tilt it, or it will take a lot of what you call effort to what you call trip it down. But whereas this is it's almost like a point, right? So with a slight movement, the center of gravity is going to be away from the base. Now, the same concept, even in the Leaning Tower of Pisa, yes, suppose thinking that this is the center of gravity and it should fall into the base, then the chance of what you call destabilizing is quite what you call remote. Now it is like this. Frankly speaking, just you Google it and you will have all that information. When they have reached to the 8th floor itself, it started leaning. Okay, and it is almost like from the straight plumb, I think it is about 4 degrees or 5 degrees, it already started tilting. Now the engineers or whoever is the what you call the team, they try to bring that particular what you call center of gravity, that line, to fall within the base. So that is the kind of repair they have done it, so that it is still intact. Okay. Now, why I am saying all this? To have an idea, in today's class, we are going to go with center of gravity. See, one is mathematical calculations. That is a procedure which you are going to adopt in your what you call study. That's okay, but you have to know why you are doing it, or what is the usage of that particular concept in your what you call architectural profession. I shall give you one more what you call example, which you will come across almost day in and day out. Say, for example, this is a tree. Okay, there's a big branch. Okay, you want to tie a string. I think there is nothing. I am not bringing any mathematics or anything here. Where will you tie the string? Will you tie it here? Will you tie it here? Or will you tie it here? Where will you tie it?
In the middle, sir.
Pardon me?
In the middle, sir.
Near middle. Why you don't say what you call tie it here? Come on, see, your answer may be silly, but still you can tell. You can see, if you come out with some answer, probably I think I can explain mine much more in a better fashion.
Maybe because it's weak, sir.
It's weak. Okay, you started with the word weak. Okay, just bring it back into the technical terms. Okay, when you have a swing, or for that matter any other item, how does it behave? It is suppose if it is a straight line, it starts deflecting. Will you agree with that? The branch will try to deflect, right? Yes or no?
Yes, sir.
Okay.
Yes, sir.
If it deflects, what kind of a feeling will you be having if you are sitting in this swing? Come on. If the swing is at this particular place, and you are making use of it, and is going to deflect, what kind of a feeling will you have?
Maybe like
It's going to break.
Yeah, it is going to break. Okay. Now, when it bends, there will be bending stresses. Okay, you are not new to the word stress. Okay, so the bending stresses at this particular point is something different. If you tie it here, it will be something different, or if you tie it here, it will be different. So the bending stresses across will be definitely varying. Okay, I shall just stop it there. Come back. Say, as an architect, you are trying to take up a project. Okay, a kids park or some kind of a recreation center. Okay, I don't know whether you will be able to visualize this. Suppose in a play area, you have been asked to design swings. Again, I take the same example. Here it is a tree, but here it is a swing. Okay, there will be a two-legged frame on both the sides, which will be fixed, and there will be a rod, or there will be a horizontal bar or a horizontal beam, for which you will be putting the swings. Okay. Is this picture? Can you just imagine?
Yes,
In a park or in a
Yes,
play
sir.
center, for kids to use the swings. Can you visualize this?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Now, it is your responsibility. What is the weight of the kid? We don't know. See, you have to ask. So, for example, that particular park could be the kids may come, or this may be used by somebody else who are not in the smaller age group. But anyhow, you will be having some idea what could be the weight. Okay. Ultimately, when it is going to do this, and how much should be the diameter of the, either it could be a rod, that means a circular cross section, or it could be a rectangular cross section, or it could be a square cross section. But you should know ultimately you will be asked to design what is the dimensions of this particular horizontal member, and which particular cross section will be in a position to take care of any other design parameters, design constraints. Okay, now I'm just putting it very broad. Okay, suppose you have such kind of a constraint. Now it is your responsibility to come out with which particular cross section is going to be suitable here, and within the given stresses, whatever within the given serviceable conditions, you have to design it. For that, you require this kind of parameters. Okay. See, again, I'm not saying that you have to do these calculations in your office. See, you may be having a what you call a design team, but you should be aware when this kind of a situation, what you call crops up. Okay, you can have what you call a chance to play with different cross sections and to get the stresses as minimal as possible, and to the deflections should be as less as possible, so that the users can feel comfort and the feeling of safety rather than having an anxiety. If I sit, this may break. No, such kind of things should not. Now, are you understanding now what is the what you call where we are going to use these kind of what you call parameters in our calculations? Is there anything that is what you call not clear? Please tell me. I can say these are the ultimate what you call practical applications where you require the concepts of this. This is only a mathematical what you call processes. We can just a procedure and then we can do it. But without knowing why we have to what you call bank upon these kind of concepts, I just mentioned it to what you call in the calculations of deflections or in the calculations of what you call stresses, where what you call designing the members which you require it, which you require. Okay, so now we will start with the center of gravity. Okay, before going to the center of gravity, I just wanted to clearly mention the objective of this whole chapter. Of course, I have given you some kind of a qualitative vertical aspect, but what are you are going to learn by going to this chapter? One, you will have defining the centroid for center of gravity and centroid, locating the centroid for plane areas where that position, and how do you compute the centroid for a composite shapes. Suppose example, say this is a square. Can you tell me where the centroid is going to be? Okay.
At the center.
At the center. Okay, but there could be some complex what you call shapes. Okay, where is the centroid? So this is the another objective, that finding out the centroids for a complex shape. Why, you may get a doubt, sir, what is the use of this complex shape? I don't know. See, as an architect, you will visualize certain things and then you will come out with some what you call different configuration, which from a aesthetics point of view, from a what you call what I would say, depending on that particular location where you felt, you may feel that yeah, this shape, this particular shape could give you a lot of what you call advantage, right? Or something like a square, and on top of a square there could be a triangle. We don't know. Okay, when you have such kind of a thing, you should be in a position to find out the centroid, to find out the various parameters in your design process. Okay. Next, similarly, what is the moment of inertia? And moment of inertia for a simple vertical geometries and complex geometries and composite geometries. Composite geometries. Okay, it may be what I would say may not be clear at this particular point of time, but as we proceed, you will be seeing what is those composite vertical objects, and analyzing and then finding out the centroids. and ultimately, and you will see what kind of a shape of a member will be advantage for the given situation. You may come out with 2 or 3 alternatives and choose the best among them. With that is the objective of this particular topic. Okay. Now, suppose you take this particular figure. Frankly speaking, there is nothing new in this because you have already done it, but it all depends on how you look at it. Okay, there is a mass. I'm not going to do a vertical mathematical derivation here, but I'm just trying to understand. This mass consists of number of particles. Okay, say for example, there is a particle 1, which is having a mass m1. Now, mg, you know what is the weight of that particular mass. Okay. So m1 into g. So this particular mass, the weight acts vertically downwards. Okay. Same thing, you take any point, m2, m2g, m3, m3g, m4, m4g. Like that, mn into g. G is constant. This is a force. This is a force. This is a force. I'm not talking about capital Mg. Okay, this is a force. So there are number of forces which are acting parallelly. Okay. Now, all parallel forces can be replaced by a single resultant. You are familiar with what is resultant? In your earlier semester, you read it. So that is, instead of all this, you can have a resultant which is passing through a particular point where the whole mass is actually concentrated. That is nothing but your center of gravity. So the same representation, m1, m2, m3, m4, mn, and say for example, you take this m1 point. Okay, what is the coordinate of this m1 point? Say for example, from OY axis, it is at a distance of x1, and from OX axis, it is at a distance of y1. Do you have an idea what is a moment with respect to a particular point? Can someone tell me? Moment. That is a force. m1g is a force. The weight acting downwards is a parallel, what you call acting parallel to the axis. Tell me, what is the moment? What is the definition of a moment at least? Manogna, can you attempt please? Manogna. Yeah, tell me please. What is the definition of a moment? Or anybody else can give me an answer? See, you have done it in the last
act
semester.
of moving.
Yeah, tell me please.
The act of moving or changing of position or a place.
No. I am not asking any. How do you calculate a moment? What is the definition of a moment? M-O-M-E-N-T. Force into perpendicular distance from the line of action. Don't you remember it?
Yes, sir.
Yes or no?
Yes, sir.
Then why you people are keeping quiet? Say this is a force, and I am asking you to take a moment with respect to what you call this point, this force is coming here, okay, and with respect to this particular point, what is the distance? This is x1. So m1g into x1. Similarly, you take this is the perpendicular distance on the x-axis, and this is the perpendicular distance on the y-axis. If you take with respect to O and about this particular axis, it is O, it is y1. So m1 into y1 into g. So both the sides, the g will be there, so it is getting cancelled. So for every particle, you are taking a moment m2 x2g, m1 x1g, like that, is equal to, it is a resultant. If you sum up all the particles, that should be equal to the mg here, mg x bar. So g and g and all, both the sides gets cancelled. You bring m this side, so x bar is equal to that particular value. Now, I think, I don't know whether you are understanding what is the concept of a moment or not, but we have done it earlier. Okay, let me just bring back that into. Okay, for a while, just take this. There is a 20 Newton acting at a distance of 5 meters, and there is a total is 15 meters. Okay, and there is 3 meters distance here between B and C. 5, 3, 8. This will be 7. Now, what is RA and what is RD? Now, take moments with respect to RA, with respect to A, sorry. Okay. Now, what are the forces? RD, take moment. Moment means what? Force multiplied by the perpendicular distance. So, RD into 15, which is taking in a counterclockwise, is equal to 10 into 8 plus 20 into 5. Now, what are we doing here? You are taking the force, and see, this is the line of action. So the distance between the line of action, the perpendicular distance between the line of action and the point of consideration is the moment. This is what you have done it, and I do not know why you could not answer it. Is it clear?
Yes, sir.
So the same moment, you are taking it with respect to a force that is actually a small particle m1 into that particular distance x1. Same thing, m1 into what we call this y1, this particular distance in both the directions, x1, y1. Say for example, if you want to have what is the what you call centroid. Suppose if I say this is the centroid, it will have an x coordinate, it will have y coordinate. So that is what we are trying to figure out, x coordinate and y coordinate. Okay, you may have some confusion, but nothing to worry. If you solve a problem, the confusion will be what you call, you can clear it off. But you please try to understand the concept of movement. You already know the same concept is utilized here. Okay, is there any doubt, so that I will repeat?
No, sir.
Is it clear? Okay. So this is about the center of gravity. Okay, but you take a plane area like a triangle, rectangle, plane area, a lamina. We call it as a lamina. Okay, for that we what you call take it as the what you call the center of area of such kind of lamina is known as centroid. So centroid is basically deals with the area. Okay, that you please keep it in mind. when it comes to area, the same concept. I'm just simplifying the same formula. I'm not keeping the mass, I'm just keeping the area. Suppose x bar is equal to sigma A y sigma total area. The same thing. Sigma AX by total area, I will call it as A. Now, here it is the mass area. Here it is my m2y. Instead of mass, it is area and the y. And instead of mass, it is area and x is x. Okay. So these are the two things which you may have to remember when you are finding out the centroid for a simple lamina. Okay. Quickly, I will just show with an example so that it will be clear to you. Just note down the problem. Find the centroid of the lamina shown in the figure. Centroid of the lamina shown in the figure. Okay, suppose this is in a simple terms inverted T section. T is generally it will be like this, but it is inverted. Okay, inverted T section, and we call, okay, just you have to remember the terminology properly. This we call it as a flange, F-L-A-N-G-E. You should use the correct terminology. And this we call it as a web, W-E-B, web. Okay. Now, the flange width is 150 mm, and the web depth of the web is 100 mm, and the thickness of the web is 20 mm, and the thickness of the flange is 20 mm. Okay. I'm just taking A, B, C, D. A, B, okay, and C, D, E, F, G, H. Okay. Now, find out the centroid of the plane lamina. First thing, just tell me, is it symmetric with respect to x-axis and y-axis? Is it symmetric to both the axes? Okay, you may get a doubt. How to check whether it is symmetric or not? Suppose if I draw an imaginary axis, you just see, is it symmetric on left side as well as right side? Is it one and the same? You have to tell me. Yes. So it is with respect to what you call vertical axis passing through the section. Yes, it is symmetric. And is it symmetric if I draw? Is it symmetric with respect to reference x-axis?
No.
It is not. So the first and foremost thing, if you what you call are clear, say for example, it is very simple. You take a rectangle, and is it symmetric with respect to x-axis and y-axis? I'm talking about this.
Yes.
It is. Say you take x-axis, this half, exactly similar. You fold it, it will become one. Same thing. You take, forget about x-axis, take y-axis, and again you fold it, they will match. So that means this particular lamina is symmetric with respect to both these reference axes. So that means the centroid will lie at the intersection of those axes. It is very simple. Whereas when you have, it is symmetric with respect to only the vertical axis, yes, that means the x coordinate will be what you call, only you will have the centroid will be along this particular vertical axis. It may lie here, or it may lie there, it may lie there. That position we may have to find out. But whereas the x is always, because see, you take this as x. That is, x coordinate will always be 0 here, whereas y coordinate, it will vary on this. So your objective is to find out at what height. So you will, here we are finding out x bar and y bar. There is no x bar in this case, but you will try to figure out y bar. Is this clear? In some cases, the y bar will be 0 and the x bar will be there. And in some cases, you will have both. So we will see all the types of problems so that you will have an idea what exactly the centroid and how do you find out the coordinates of the centroid. Now, is this clear? We haven't finished the problem. It will be simple. But what I mean to say is, if the given lamina is symmetric with respect to both the axes, then it is the centroid lies at the intersection of the both the axes. If it is what we call symmetric with respect to a vertical axis, then the x coordinate will be 0, the y coordinate will be along the centroid will be along the vertical axis. And if it is symmetric with respect to the horizontal axis, then it will be only the y-axis will be, y coordinate will be 0, the x coordinate will be along the horizontal axis. Okay, now we will see. Now you make, because you just see this is one rectangle and this is another rectangle. So you make two rectangles, and A, B, C, D, and another one is E, F, G, H. E, okay, like that. I will just close this. E, F, G, H. Okay, what is your formula? X bar is equal to sigma A x by sigma A, and y bar is equal to sigma A y by sigma A. Okay, now take the first one, area, sigma area. So find out the area of ABCD, find out the area of EFGH. 20 multiplied by 100. 20 multiplied by 100. I'm just putting it as area, mm square. Okay. Okay. Now you have, this is the referral axis. Suppose if I take 1, 1, my horizontal axis, and this is your vertical axis. Now, what is the distance of this particular ABCD, the centroidal distance? So for this particular thing, it is 100 mm. It is a rectangle. At what distance it will be there? 50. Okay, 50 plus there is already 20, because your axis of reference is this. Okay, so centroidal distance and you are going in a vertical fashion, so you call it as y. It is 100 by 2 plus 20, 70. Same thing, EFGH, EFGH, area 150 into 20. Okay, what is the centroidal distance? This will be at a height, so 20 by 2. That is equal to 10. So add up this one because you are having the total area, and here 20. 2000 multiplied by 70, and here 3000 multiplied by 10. Okay, this is now if the total area is 5000, right? .34 mm from the referral axis. So this is 20, and maybe approximately at this particular point, this is maybe it is 34 mm from the. Okay, it is not hard and fast rule that you have to take it from here only. If you want, you take it from there. Then you will end up with this is the distance. If you take that as your referral axis, doesn't matter. If you want, you can try. And that distance will be from that particular reference axis. Okay. Any doubt in this? Don't hesitate. See what we have done. Take the total lamina into different regular areas. So each area, the corresponding centroidal distance from referral axis, multiply, and then add up all the what you call area multiplied by centroidal distance component divided by total area. So you will get x coordinate, and similarly in the y coordinate. That is the formula series. So given lamina, we have broken it up into different regular shaped what you call units. This is a rectangle, this is another rectangle, and our referral axis is, we have taken this, but as I mentioned earlier, you can take this also as your referral axis. But this is the referral axis. From this particular axis, area of this unit we have found out. For this unit, the centroid lies to the center, so that is 50. But since the referral axis from here, it is at a distance of 20, so 50 plus 20 is 70. So this is the centroidal distance. Area multiplied by that centroidal distance, this is the one. And similarly, area of this particular unit, same thing, and it is at a distance of 20 by 2, 10. And this 3000 multiplied by 10 is 30,000. Summation, and divided by 5. You will not have x bar because it is symmetric with respect to the y-axis. You will have only the y coordinate. So the x coordinate is actually here itself. So it is a 0. That's it. Okay, there is nothing. It is lying on the referral axis. I shall just tell you. Any doubt? Okay, before I give you a problem, any doubt on this? Okay, we may do a few more problems, but is it clear, or do you want me to repeat it again?
Clear, sir.
Clear, sir.
Okay. Say, for example, I won't solve it now. but I shall just give you. Is it symmetrical with both the axes or not?
Symmetrical, sir.
Symmetrical with both with respect to horizontal and vertical axis. Okay, I'm just don't bother about these dotted lines. I have done it for some other purpose. Okay, there is a rectangle. Out of this rectangle, a small portion is pulled out. It is hollow, empty. This is the cross section. Now, is it symmetrical with respect to x-axis and y-axis?
No, sir.
Yeah, like is it symmetrical with any one of the axes, or is it not symmetrical with both the axes?
Not symmetrical.
Not symmetrical
Not
in
symmetrical
any.
both axes.
Not symmetrical with respect to both axes. Excellent. So now you will have x bar as well as y bar. In the earlier case, you have only y bar, but now you will have both. Okay, this is the problem. We will solve it in the next class. Okay, and there are different vertical varieties of problems, but we will go step by step. Okay, so that you will have an idea which is unsymmetrical with respect to both the axes. With respect to one axis, it is symmetrical. So you will have either x bar or y bar. In unsymmetrical to both axes, you will have x bar and y bar. Okay, fine. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Sir.